Let's wait for 2-3 minutes. After that, I will start. Okay, let me start. So this is seventh week problem solving for advanced atmospheric physics. So first thing which we will do is this. We will try to solve the assignment 6, and this is the first thing which we will do. Second is uh, we will go for the week 7 contents. I think the next week, that is week 8, uh, probably the atmospheric physics part will end, and after that, the upper atmospheric part, which is not related to this normal dynamics of weather and climate, but related to the ionosphere and space physics, that will start. Mostly in space physics, I would say some chemical reactions will be there. We will try to look for the equilibrium things and all those things. But yeah, right now we are particularly focused on the dynamics of the atmosphere. Okay, so let's start the assignment 6 questions. We'll discuss about it, and once it is over, we will go to the week 7 contents and try to see how to solve the week 7 assignment questions and all. Okay, so let's start with the assignment 6 question. Okay, let me open it. So this is the week 6 assignment. So the first question is that for an air parcel to be convectively stable, condition for its Brand-Weissala frequency should be. So there are a couple of options, and we see that n square greater than 0 is the correct option. So why that is true? Because if you remember the formula for n square we have derived, that is g by theta of the environment d theta dz. This is what we have derived. It is n square. Remember, n is the Brand-Weissala frequency square. Okay. N is the Brand-Weissala frequency. Just remember this. Okay. This is generally greater than 0 because theta is some constant quantity. D theta dz, if it is greater than 0, we have seen that it is a stably stratified atmosphere. So it's stable atmosphere. Okay. So convectively stable atmosphere is when n square is greater than 0. Now, why? The question is why. We have discussed it, but let us do it again. We have seen that using the potential temperature formulation, the T by theta, d theta dz, is actually equal to gamma of parcel minus gamma of environment. So parcel, actually what we have written that time is dry air parcel. So gamma D. Okay. So when gamma P, that is for the parcel, if the lapse rate, that is the rate of decrease of temperature with height, if it is greater than that of gamma, that is the environmental lapse rate, then what is happening? So you have this as the temperature profile. This is your Z altitude. This is temperature. Okay. Gamma P is greater than gamma. So for the parcel, suppose, or for the environment, let's say that the temperature is decreasing like this. Let us say linearly. Okay. This is for the environment. And for the parcel gamma P, since it is greater, that means what? What is the meaning of greater? That rate of decrease of temperature is larger than the environment, right? Because gamma's definition is that, Laxnight's definition is that there is the rate of decrease of temperature. So if gamma P is greater than gamma, that means partial temperature decrease rate is much larger. That means what? It is faster decreasing. The temperature is decreasing faster. Something like this for the partial. Okay, so this is for the partial. Now, take any level. Okay, let's change the color. Take any level. Let us say this level, one particular height. Look at partial temperature. This is T of P. Look at environment temperature. This is T of P. So, what we found for this particular condition, that T of P is much less than T of P. And according to the ideal gas equation, for a constant pressure, if you don't want to use, so actually the density is proportional to inversely proportional to the temperature. Okay. Generally at constant pressure. But let us say that the pressure is constant at certain these 2 points. Why? Because remember the definition of the partial assumption. Wherever the parcel is, the pressure inside and outside should be the same. It immediately equilibrates. Okay. So for that, you can have this density is inversely proportional to temperature. Now, since Tp, temperature of the parcel, is less than the temperature of the environment, density of the parcel becomes greater than the density of the environment. And if the density of the parcel is greater than the surrounding environment density, then what will happen? The parcel will fall. Parcel will fall. That means the convection is not occurring. It is opposite to the convective activity. For convection, what will happen? There should be a rise in the parcel. Then only you will see the cloud formations and all those things. But in this case, the parcel will fall. So it will not allow the convection to occur. Okay. So that's why this convectively stable. Stable. That means no convection. This is the okay. So from this, it is much more easily visible. But actual thing changing is this d theta dz. Okay. So here gamma p is greater than gamma, p and theta being some value constant, d theta dz is actually greater than 0, which is here also. The same thing is present here. Therefore, n square should be greater than 0 for a stable atmosphere. Okay. This is the first question, explanation of the first question. Let's go to the second question. A layer of unsaturated air flows over the mountainous terrain, in which the ridges are 10 kilometers apart in the direction of the flow. The lapse rate is 6.5 degrees Celsius per kilometer, which is commonly the environmental lapse rate, and the temperature is 20 degrees Celsius. For what value of the wind speed u will the period of the orographic, that is terrain induced forcing, match the period of buoyancy oscillation? Fine. There are so many information which are given. So let us see one by one that. So one thing is that the buoyancy oscillation, which is nothing but the Brandweiss-Waller frequency. This is the buoyancy frequency. Okay, this is the buoyancy frequency. So the time period of the buoyancy frequency or buoyancy oscillation will be 2 pi by n. This is the general definition. Okay. Generally, it is 1 by n, but we are looking it in uh, what do you call as the frequency is kind of an angular frequency kind of a thing. Okay, so we are writing it like this. And suppose there are two regions and you have 10-kilometer distance to cover, which is being asked in the question. So you have some x is equal to 10 kilometers, the distance between the two regions where the motion is there. Okay, and we need to find out uh, the velocity with which the air is moving. So for that we know, and it has been already asked that the time period of this motion should match the buoyancy oscillation. So T should be equal to capital T. And how can we write T? Simple definition. That is your x, the distance between the two regions, divided by the velocity. That should be equal to the T. That should be equal to 2 pi by L. Alright. Now U is what I require. So it should be Nx divided by 2 pi. And now if you write, now how will you find out N then? That is another question. But x is known, so n times x is what? 10 kilometers. Make it in SI units and divide it by 2. Simple. So I need now n to find out what is the velocity of the flow. Okay. So let's do how to find out n. We have several formula for n. One of them is this, right? G divided by t into t by theta d theta dz. See, what I'm doing is that actually n's formula is this one. What I am doing is that I'm multiplying by a t and divided by t. That is what I have done. See, I have multiplied and divided by. So tt if you cancel, you get this. Right? So now, what else we can do? Now, this we already know. That's why I have done that. So what is that? Root over g by t. T by theta d theta is that is gamma d minus gamma. The dry air parcel lapse rate minus the environmental lapse. So N will be your G is given 9.81, T is given how much? 20 degrees. The T is given to be 20 degrees Celsius. But whenever we are calculating in the atmospheric physics or any uh, thermodynamical physics, you should use the Kelvin as the SI unit. So it should be 273 plus 20, which is equal to 293. All right. So you can put it here 293 Kelvin, and you have this gamma T minus gamma, which is approximately about 3.26 into 10 to the power minus 3, okay, degree Kelvin per kilometer, meter, sorry, because I have taken 10 to the power minus 3. Okay. So even if it is degree Celsius per meter, that is also fine because it's a change in the temperature. Okay. So how it is happening? Because your gamma D, this is a constant which one must know, which is about 9.76 degrees Celsius per kilometer, and your gamma is 6.5 degrees Celsius per kilometer, which is given. This is the environment. This is given. But the gamma D, one must know. So it is known, I would say. Okay. So based on that, if you can calculate, okay. So what you get finally is that if you do all the calculations, taking the roots, you will get 0.0104, something like that. Hmm. Okay. So this is what you are getting. And yeah, so N is generally in radians per second. So that's why the 2 pi we have used. Okay. So U therefore is 0.0104 into 10 into 10 cube, which is 10 kilometers in meters divided by 2. When you do this, all the calculations, you'll get around 16.62 meter per second. This is the answer. Okay. So in this part, in this question, gamma d is not given, but it is assumed that you know that gamma d's value is about 9.76 degrees Celsius per kilometer. It varies little bit. It will vary based on the moisture, but it remains almost same. Gamma is given, environmental temperature absolute is given, temperature is also given. So we have all the quantities. Only thing is that we don't have the theta. So that's why we have to make this arrangement. Okay. So that is what we have made. Okay. So next, let's go to the third question. So it is nearly 16.5 meter per second. Third is, if the potential temperature theta increases with the increasing altitude, then with respect to the displacement of the unsaturated air particles, the atmosphere is very simple. D theta dz is greater than 0. Theta increases with the increasing altitude. D theta dz is greater than 0. So it is a stable atmosphere. We have discussed this, right, in the first question. So d theta dz is given to be greater than 0. In that case, we have seen that it is a stable atmosphere. So it is already, we have discussed in the first question. Okay, so it's a stable atmosphere. Fourth, suppose unit mass. So 1 kg parcel of dry air is rising at constant vertical velocity. If the parcel is being heated by the radiation at the rate this, what must be the speed of rise B to maintain the parcel at constant temperature? That's the question. Let us read it again. 1 kg of parcel, which is a dry air, rising at constant vertical velocity. If the parcel is being heated from the surface at a rate of this, what must be the speed of rise? That is the vertical velocity. Uh, how much will be the speed if the parcel maintains a constant temperature? That is what is the question. So remember, we have done so many equations in your atmospheric uh, physics. Which equation do you think that will be used up here? Where you see that there is a dry air parcel, there is a vertical velocity. Okay, there is a dry air parcel, then there is a vertical velocity, and also there is a radiation rate which is given. So what we can do is that for the fourth question, the same we have seen that W is there, there is a comment on W, then there is a comment on the radiation rate, right? The radiation rate. So the first equation which comes to my mind for solving this kind of a question must be the thermodynamic energy equation. That is the only equation which consists of the heating rate or the radiation rate, thermodynamic energy equation. And what is that? Simple. From the first law of thermodynamics, Cp dt minus alpha is the specific volume. dP is equal to Q. We know that. Okay. Now, if we differentiate it with respect to time, we are getting the thermodynamic energy equation, which is RT by P, dP dt, which is equal to dQ dt. See, here comes the heating rate or the radiation rate, right? Rate of change of the heat or radiation. Okay, so fine, this is okay. And what else? Let us call this as some J, the heating rate. All right. So let us then write it. dt this minus. You have RT divided by Cp. P dP can be written as dP dz and dz dt. Okay, and this is your J by C. Because Cp I have divided from all the sides. Okay, so now you have dt dt minus RT by CPP. dP dz is minus rho g from the hydrostatic equation. This is W J by C. Cp. So rho and RT by P, they are opposite to each other. So this can be cancelled. Minus minus becomes plus. So dP plus G by Cp into W is equal to J by Cp. Okay. Now it has been asked that it maintains constant temperature. There is no uh, specific mention that it is constant with time, but we will assume that it is constant with space as well as time. So let us make this as 0. Okay. What you left behind is G by Cp, W is equal to J by Cp. Again, Cp will go. So what you will finally get is this. W is equal to J divided by G. G you can take it as 10 meter per second square for simplicity. So you get 10 to the power minus 2, roughly 1 centimeter per second. Okay. If you take 9.81, it comes out to be about 1.02 centimeter per second. So this is how you should approach this particular question. Let's go to that again and see. So it's 1.02 centimeter per second. So you understand that how we proceed. So when you have a question, just check what variable is being mentioned in this question. So based on this radiation at the rate of 10 to the power minus 1 only, I can quickly recall that it is the only the thermodynamic energy equation where this heating rate or radiation rate is there. So we must use that and apply this that to maintain the parcel at constant temperature. And it is not said that whether it is with time, space. So we will assume that both. Let us say that the entire temperature is constant with time as well as make it zero, make it much more simplified, and that is how we proceed. Okay, and it's a 1 kg parcel, so you don't need to worry about the mass. Okay, next is the fifth question, that is an air parcel that has temperature 30 degrees Celsius at 1000 hectopascals is lifted dry adiabatically. What is the density when it reaches the 500 hectopascals level? Okay. Again, there are many informations given in this question. Let us list it down and try to solve it. Okay. So, what are the informations given? Temperature is of the parcel is 30 degrees Celsius, which is I have already told that don't use degree Celsius, use always Kelvin. Okay, because that is the SI unit. P1 that is 1000 hectopascal given. P2, the second level is 500 hectopascals. Okay. This is that what will be the change in the density. So let's go to the question again. Has a temperature this at 1000 hectopascals is lifted dry adiabatically. What is the density when it reaches 500? So a parcel is here, which is 1000 hectopascals, almost near the surface. Its temperature T is 303 Kelvin. Okay. Now this parcel is lifted dry adiabatically to another level P2, which is equal to 500 hectopascals. Tell me what is the density variation? That is, what is the density rho 2 here? That is the simple question. Okay. Now, remember, this process is dry adiabatic, and we have discussed in the last class that dry adiabatic process, for dry adiabatic process, what is that quantity, the thermodynamic quantity which is conserved? Theta. Potential temperature is constant. And what is the definition of the potential temperature? Is simply T into P naught by P to the power R by Cp. What is R by Cp value? Is we have also seen this 0.287. What is P naught? Generally it is taken as 1000 hectopascals. So theta is constant, therefore let us say that T2 is the temperature over this P2 level and T1 is this. Okay, so what we can write, if this theta is conserved, we can write T1 P naught by P1 to the power R by Cp should be same as T2 conservation. So this should be this is R1. Fine. Now next is what? Let us see. See, if you get T2, you know the pressure, you can calculate the density easily. Okay, so let's find out T2 then. So T2 should be what? T2 should be P1 P naught by P to the power, sorry, P1 to the power R by Cp divided by P naught by P2 to the power R by 6. So T2 will be equal to T1, P naught to the power R by Cp and P naught to the power R by Cp will cancel, and there is a reciprocal of P2 by P1. Right? This is what you will get if you solve T1. So T2 will be equal to 303 Kelvin. P2 is what? 500 hectopascals. You can convert into pascals, but doesn't matter. It is in the ratio. So you can keep it in hectopascals and 0.2 meters. That's all. So this will be 1 by 2. So you do this 303 divided by 2 to the power 0.286. So once you do that, it comes out to be about 248.3 Kelvin. The T2, that is temperature at 500 hectopascals. And I need rho 2, which is density at 500 hectopascals. So it is P2 divided by R into T2, R into X. Okay, so P2 is, now you have to put in pascals, 500, 1000 pascals, 100 pascals, and this is 287, this is a known value, and this is 248.3 Kelvin. If you do this, comes out to be 0.702 kg per meter. This is the answer. Simple. Concept is dry adiabatic lifting. Their potential temperature theta is constant, and just use the conservation, and you will get the results. Okay. Another thing is we have used ideal gas now. Ideal gas. Okay. So these are the two basic things which is required to solve this problem. All right. Let's go to the sixth question. So 0.70 is the correct answer. If one moves towards poles at a constant height, weight of the atmosphere above that person keeps on. When we have looked using G dash, effective gravity, we have seen that your G dash generally increases towards the pole, right? Because we have found out that G dash is equal to G minus R omega square cos square phi. When phi is 90, that is poles, G dash becomes equal to G. So it is higher than the poles. So we must think that it is increasing. But the twist is that towards the poles at constant height, weight of the atmosphere above that person keeps on. So how will you do that? So one of the ways which I have thought, there can be many ways, I don't know, but what I thought is that this can be one of the possible things. See, for the pressure coordinate, we have our hydrostatic equation delta phi by delta p is equal to minus RT by P. Right? This is what we generally have. Okay. Now, yeah, minus delta phi by delta P is equal to minus RT by P. Or you can keep it alpha also for your, or make it RT by P. That is fine. Minus RT by P. Okay. Now, what is there is that now if you take delta phi here and you put minus RT dP by P on the other side. Okay. And let us say that phi starts from 0, that is from surface, some height phi naught. And this will start from the P at 0 to some P at 1. Okay. So what do you get? This is phi naught, which is at a constant height. Okay. And this is minus R T log of P1 by P naught. Right. This is what you generally get. Now, if you have your phi naught here and RT log of P naught by P1. Okay. So now this P naught is generally greater than P1. So this part becomes positive. All right, this part becomes positive. Now, on the other side, we have phi naught divided by RP is log of P naught by P1. Okay, now this phi naught, let us say that this is constant. Now, if temperature decreases, which is towards the poles, okay, towards the poles, temperature decreases, this part keeps on increasing, right? Temperature is the denominator, so it keeps on increasing. That means what? That means if this part increases, that means log of P naught by P1 also keeps on increasing. It becomes much, much higher, right? So now log of P naught minus log of P1 is greater than 0. Look, this difference is increasing. Surprisingly, I don't know why the answer is decreasing. I'm not sure. But I, what I have got is that it keeps on generally increasing. But if you go to this, like log of P naught is greater than log of P1, right? So at some height, okay, so P naught is there where phi is 0, and this is phi naught, right? This is P1. So at this height, if you see, the pressure decrease is much larger. Okay, this decreases, or P naught is much, much larger than this. Okay, so I'm not very sure that why this uh, near the poles, the pressure or the mass of the atmosphere should decrease. This is not very clear to me, but in general it increases. With G dash definition also it increases. Number one. Number two is that uh, what you call as, if you look at the surface pressure at the poles, surface pressure at the poles, that is also very high. So high pressure means what? The mass of the atmosphere above the surface is very large. So in all sense, I would believe that it should increase, but there is, I don't find any solution to this part. So I will look into it. Why the answer is decreasing? They have given, uh, and probably let you know. Okay. So right now, what I have thought that time also, that is, it should be increasing. Okay. So this I will check once and try to show you. Yeah. हाँ हाँ वो तो होगा ही ना ग्रेटर. हाँ वही मैं बोल रहा हूँ. हाँ सरफेस पे तो ग्रेटर होगा ही ना. जितना हम नीचे जाएंगे उतना ग्रेटर होगा ना. प्रेशर है प्रेशर. क्योंकि कॉलम भी बढ़ गया ना, इतना कॉलम भी बढ़ गया. इससे पहले जब हम लोग प्रेशर यहाँ पे निकल रहे थे तो इसके ऊपर वाले कॉलम में था. अब ये एक्स्ट्रा हो गया तो वो तो बढ़ेगा ही. बट इन टोटलिटी ये पी नोट जो है वो डिक्रीज क्यों कर रहा है दैट आई डोंट नो. मतलब मुझे तो लग रहा है कि इंक्रीज करेगा बट आई एम नॉट वेरी श्योर. हाँ एग्जैक्टली. पता नहीं. लेट्स सी. इसको देखूंगा मैं. आई विल लुक इनटू दिस. The next question is the seventh one. For a purely horizontal gravity wave, its frequency will be okay. The next two questions is similar. So seventh and eighth. Let me draw a simple figure to understand, to make you understand the thing. Uh, this is related to the internal gravity waves. So suppose you have something like this. Okay, two different heights. Let's say z and let's z plus delta z. Okay, and this is your normal. And suppose this is the phase of the gravity wave. This is the alpha from the normal. Okay, this is phase. one of the phase of the gravity. These are all internal gravity. Just remember this. Okay, so this is some phi. Okay, I'm sorry, this is not phi. Phi is the phase, but this is delta S. Suppose this is phi. All right, and okay, so this is delta Z. We have already seen this. Okay, make it small. Okay, now we know that this is now delta Z. So delta Z, this is 90. Okay, delta Z by delta S is equal to cos alpha. This is known. Also, delta Z can be written therefore as delta S cos alpha just from this trigonometry. Okay, now your buoyancy oscillation is minus n square delta Z into cos alpha. For what? For this one. If your buoyancy oscillation is happening over here at a slanting angle, then it should be minus n square delta Z into cos alpha. Because we have seen that suppose this is your Z direction and your buoyancy oscillations are happening in this plane, then it is d2 by dt2 delta Z is nothing but equal to minus n square delta Z. Right? Which we have seen. But right now, instead of vertically moving, it is now slightly slanted by an angle alpha. So it should be like this. One was here, now it is here. So this is now cos alpha. Can I write this? That minus n square delta S cos alpha into cos alpha. Remember, this is nothing but delta Z double dot. Delta Z acceleration. All right. So delta Z double dot. Finally, you are getting minus n cos alpha whole square delta S. Right? This is what you are getting. Or I would say that you can keep it delta S double dot because it is happening now. The acceleration is happening here. So you can keep it like this. So what is happening is that for now for horizontal gravity wave, horizontal gravity wave, your oscillation, buoyancy oscillation should be absolutely vertical, should be in Z, not in S, should be in Z direction. That is here for a horizontal gravity wave which is propagating in some horizontal direction, its oscillation should be in the Z direction completely because it is a transverse wave. So it should be in Z. In that case, your alpha should be what? It should be equal to your what do you call it? It should be zero, right? So your alpha should be zero. So if alpha is zero, then what is your frequency? N. Therefore, the frequency should be equal to N in case of horizontal. But for non-horizontal case, for non-horizontal gravity wave, the oscillation should be might not be in some S direction at some alpha, then it should be the frequency should be equal to n cos alpha. And cos alpha generally varies between what? Your particularly from 0 to 90, right? So it should be between 0 and 1. This should be the thing. So let us go there and let's see what are the options. For purely horizontal gravity wave, we have seen that it is equal to the Brandt-Weissel frequency N. And for non-horizontal gravity wave, it should be less than, always be less than the Brandt-Weissel frequency. Here, if cos alpha equal to 1, it is N, but otherwise, it should be less than that. Okay, so less than the Brandt-Weissel frequency because the frequency is in cos alpha. Okay, so this completes the assignment questions for this week. We can now move to the Week 7 content. So first we will see the general circulation model. General circulation model. Okay, just give me a second. Okay, so let's come to the general circulation model. So I have to make, okay, so this is the Earth, and on the center you have this equator, okay, and I will take a latitude, say 35 degrees north and 35 degrees south. I will take another latitude, which is about 60 degrees north and 60 degrees south. And finally, at poles, which is 90 degrees south, and here 90 degrees north. Okay, so this is north and this is south. Okay, simple. This is known to us. Now I will separate some regions. At the equator, we have low pressure zones. So I am shading it like this. Okay, another low pressure zones happens over this 60 degrees north. Okay, and 60 degrees south. So this red are the low pressure zones. Now we have high pressure zones over the subtropical latitudes. That is about 30 to 35 knots or 40 knots something. Okay, so I'm making it in dots. So these are high pressure regions. Okay, and over here also you have at the poles you have high. That is what I was discussing in that question also. Okay, so these dots represents the high pressure region. Okay, so this is what your pressure pattern looks like. Now, if this is now the pressure pattern where you have low near the equator and at 60 degrees north and 60 degrees south, then how the circulations will look like? We know that wherever there is a low pressure region, there is an ascending motion, and where there is a high pressure region, there is a descending motion. So based on that, simply based on that, we can write or we can make the direction of the winds something like this. So it goes up and it falls over here. Similarly, in the southern hemisphere, it will go up and falls over this region because these are the high pressure belt and this is the low pressure belt. Similarly, there is must be some ascending motion from here also because this is a low pressure belt. So it should go here and it should fall here. Again, it should go here and it should fall. Similarly, in the southern hemisphere, right, like this. Okay, so this is the ascending motion. You can see over the equator because of the low pressure formation. And since there is a high pressure at the subtropical latitudes, there is an entire descending motion. But again, it is ascending somewhere, right? At the 60 degrees north and 60 degrees south. We will discuss about this, why it is happening. Okay. But this is the vertical motion of the general circulation model. But what is happening horizontally is something like this. So let's change the color. Try to make it. So this is a high pressure bed. This is a low pressure bed. Originally, the wind should be like this from high to low pressure, but because of the Earth's rotation, there is a Coriolis force, and we have discussed that in the northern hemisphere, the Coriolis force deviates the winds to its rightward direction. So, if the wind is coming here, just sit on top of this arrow and see where is its right direction. The right direction should be here, right? Just visualize this. So, your winds, general winds, should be like this. Okay. So you can see that these winds are generally called as the trade winds. Okay, these are called the trade winds, and so these are surface near surface winds are called the trade winds, and its direction is not southward or northward, but it is somewhat tilted towards the east or west. Okay. Similarly, from the in the southern hemisphere, instead of going like this, it should be like this. But Coriolis force deviates in the southern hemisphere in the leftward direction. So it is like this. So the winds will be like this. And look at this. At the equator, what is happening? The winds are converging. Because the winds are converging, there is an upward motion here. See, there is an upward motion. And there is a downward motion here. So if you now look at this, this is a high pressure belt, this is a low pressure belt. Wind should be in this direction, but it will curve towards it rightward direction because it's the northern hemisphere. So the winds are like this. And you can clearly see that there is a divergence over this region, right? Winds are going in this direction, winds are going in this direction. So there is a descending motion. There must be continuity always. If there is a high pressure belt, there is a divergence in the lower atmosphere and convergence in the upper atmosphere. See, there is a convergence in the upper atmosphere. But here, since it is a low pressure belt, convergence in the lower atmosphere, there is a divergence in the upper atmosphere. See, winds are diverging. Similarly, near the poles also, it will be like this because this is high, this is low. And here it will be like this. And it will be like this. So this is totally in total called as the general circulation model. But this is the average picture. Just remember this is the average picture. Annual average picture looks something like this. Still it will not look because there is a surface inhomogeneity. Somewhere there is a high pressure region, somewhere there is a low pressure region. But in general, average and ideal generalized model, this is how it looks like. Okay. But with season, it changes. This low pressure belt with season, like in summer, moves more towards the north. Similarly, in winter, it moves more towards the south. Okay, which is called as the IT season. Fine. So this is fine for now. And so what you see is that here in this particular region or in this region, so equator to 30 north or 30 south, you find generally easterlies, northeasterlies, northeasterlies. Why? See, this easterlies, there is a this is a term which represents that winds are moving from northeast. Okay, from northeast is called as the easterly. So if we say that there is an easterly wind, that means moving from east to west. Okay, just remember this. So let me write it. Easterly means from east to west. That means direction should be negative. U should be negative. Okay. Similarly, westerlies means from west to east. Okay. Similarly, northerly means from north to south, and southerly means from south to north. Just remember this. Okay. What else we have? Yeah, the convergence and divergence. Look, suppose this is your atmospheric column at a particular region, okay, and you have a low at the surface, low pressure at the surface. Then, as I have told you, the winds will converge over here, and there will be a cyclonic circulation, of course. Winds will converge, and where it will go? It cannot penetrate the surface down, right? The winds cannot penetrate the surface. So where it will go? It will go up. So you will find that there is a very strong vertical updraft or vertical motion. So strong vertical motion. Okay. And at the upper atmosphere, there will be divergence. It has to happen. And if there is a divergence, there will be a high. Okay. This will happen. Why? Because of the mass continuity. Okay. Why? Because if in the upper atmosphere there is a low and there is a lower atmosphere there is a low, then there is a convergence here, there is a convergence here. There is upward motion here, but there is a downward motion here. So mass will pile up here, which will not possible, which is not possible. Right? Mass piles up. Not possible. Right? It is not a very stable kind of a system. So this is how it looks like. So what we have found out so far that low pressure region have cyclonic circulation. Okay, number one. Number two, winds converge. Number three, strong ascending motion. Okay. Number four, upper atmosphere divergence. Upper atmosphere divergence and formation of high pressure. Upper atmosphere. Remember. Okay. Let me write high pressure. High pressure is there, then only there is a divergence. Okay. Now you can ask me that if there is a cyclonic circulation, so suppose this is your loop, okay, and there is a cyclonic circulation. This is a cyclonic circulation. Correct? Then how the winds are converging? This is rotating. Cyclonic circulation means what? It is rotating. Then how it is converging? This is converging because this is converging because of the friction. See, this low pressure is near the surface, and near the surface there is the strongest friction. This friction helps the winds not to move straight like rotate like this, but to converge here. Okay. So with a tilted angle towards the center. This results into convergence and it goes up. Okay. Now, another thing, you are saying a strong ascending motion. Now, assume that these are oceanic region. So, winds which are coming from here will carry some moisture with it. Now, when it goes up, that is strong ascending motion is there. So, the moist winds tends to go up, right? There is an ascending motion. Now, when the moist air goes up, it cools here because temperature decreases as you go up. So, when it cools, it forms, the condensation takes place and cloud formation happens. Okay, so this region is low pressure regions generally associated with clouds and precipitation, rainfall. Okay, so generally, whenever I have already requested all of you to check the windy weather map or IM Indian Meteorological Department weather map. If you are interested in this field, you will find that whenever you have this low pressure kind of a circulation, that is this anti-clockwise, right? Anti-clockwise, anti-clockwise or cyclonic circulation, circulation of the winds. you will find that those regions are mostly having higher precipitation or higher rainfall. Okay, so these are the common points for the low pressure region. Similarly, high pressure region will be much more dry. Okay, so it is much more dry. Why dry? Because there is a descending motion. Okay, descending motion. Divergence is there. Low level divergence. Low level divergence. Okay, so this is if you, this is your column, this is your height. So there is a divergence, okay, in all directions. Again, because of the friction, there is a divergence like this. In the column, therefore, there is a descent. So there is no chance of cloud formation because winds are going down, the temperature increases. It is drier. But in the upper atmosphere, there is a low pressure which will converge. This low pressure has to form because of the mass conservation. That's all. That's why if you just look into your atlas or maps, you will find that these 30, 35 degrees north, these are the regions where we typically get deserts, both in the southern hemisphere, like in Australia, we have deserts. We have our Indian desert, Thar in Rajasthan. That is also a desert which is almost near 30 degrees north. Not exactly 30, but 20, 25. Okay. And then as you go toward Africa, there are many desert regions. So that lies in that particular band. Okay. So this completes the general circulation of the atmosphere and the convergence and divergences. The next is about the air masses and France. Hmm. हाँ, ऑस्ट्रेलिया का जो वेस्ट पार्ट है वहां पे भी डिजर्ट रहता है यही बोल रहे हो हाँ 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 जनरली जनरली हम लोगों को दिखता है कि वेस्टर्न पार्ट्स में ही ज्यादातर डेजर्ट्स होते हैं क्योंकि आ, हाँ क्योंकि जो कॉन्टिनेंट्स है जैसे ऐसे कॉन्टिनेंट है तो यहाँ पर मतलब मॉइस्चर जब यहाँ से यहाँ तक ट्रेवल करता है विंड्स लेके आती है तो ये जो रीजन है वेस्टवर्ड जो रीजन है उस रीजन में जनरली लैंड के ऊपर ट्रेवल करते करते वो विंड ड्राई हो जाता है क्योंकि बहुत ज्यादा लैंड पार्ट है ना तो मॉइस्चर ऑटोमेटिकली शेड हो जाता है तो जितना वेस्टर्न पार्ट है वहां पे ही दिखता है तो हमने इंडियन राजस्थान तो अपने इंडियन में भी वैसे ही दिखता है वेस्ट में जैसलमेर में हाँ? तो ये हर जगह का वही चीज है ठीक है ओके द नेक्स्ट पार्ट इज एयर masses and suns. Just give me a moment. Okay. So this front and all these things we generally see here at 60 degrees or mid latitudes of this particular region. Okay. So these are generally seen in subpolar low pressure pressure region. Generally extending from 45 north to poles towards 90. So mid latitude phenomenon. This we don't see in the tropics in our region, India. We don't see it. Sometimes we get a very little portion that is in the winter time over the northern parts of the India. We get some small frontal disturbance. Otherwise, we don't get it. Okay, fine. So, what is an air mass? Simple, large volume of air. These are simple definitions. Okay? Large volume of air that has constant properties or consistent properties of what? Of some variables like density, temperature, and humidity. These are the properties which remains constant in air mass. Okay. So consistent properties with respect to what? With respect to the surrounding air. Okay. Remember, so suppose this is a block of air, large volume of air, where here the temperature, density, and what I mentioned, relative humidity, RE, relative humidity. This almost remains constant. But remember one thing, vertically it may vary. Vertically, temperature, rho, relative humidity may change. But at an average, on an average, over this particular air mass, these three variables are generally constant compared to the surrounding air mass, like here. Okay, this is what we define an air mass as. So, in general, in winter, we have generally cold and dry air mass. Okay, people have noticed that during the winter time, things becomes drier. Okay? Our skin becomes dry and all those things because the weather is something like that. So, in generally in winter, we generally have cold and dry air mass. Similarly, in the summer, summer can also be warm and dry, but generally warm and moist air masses can be seen. Generally, okay. Opposite can happen. Like cold and moist can be there, warm and dry can be there. Okay. Now next is there are different types of air mass. So types of air masses. Okay. So one is that continental, tropical. Let me list it down and then I will discuss. Second is continental polar. Third is continental arctic. Similarly, you have maritime tropical. Number two, maritime polar. And number three is not there. So the arctic is not there. Okay, so this is written as the first one is smaller. The continental C is small. Tropical T is capital. Similarly, C polar C is capital like this. Okay. Like maritime, you have smaller capital T. Smaller. This is a representation. Okay. These are representations. So continental, we all know what is continental. Means over the continent when you have an air mass, and it should be over the tropical regions, our region. Okay. So that can be represented as a continental tropical air mass. Similarly, over the polar regions, if you go, it is polar air mass. Arctic was also a region which is very near to the poles. So Arctic is generally found by land. There are many land regions over there. There is no ocean there. Okay. So that's why it is continental Arctic. Maritime represents the oceanic air masses, like maritime tropical, like South and Southern Indian Ocean, maritime tropical air mass. Maritime polar go far more to the south. Okay. Third one, what which I didn't write is the maritime Arctic. Maritime Arctic does not happen because Arctic is perfectly over land, but maritime Antarctic can happen. Antarctic some portion is also land, so you cannot write it like that. Right? So, what is a typical feature? Continents are generally dry. Okay, so these are dry, but maritime is ocean, so that these are wet. This is a general feature of these air masses. Okay, and what about the temperature? Polar, of course, polar or Arctic. These are colder air mass, cold air masses. Means in terms of temperature, if you go. And tropics is generally warmer, warmer and humid. So these are the couple of things. Now, next, a very important uh, definition based on this air masses is that of the fronts. Fronts is defined as the boundary between the air masses. So these are all definitions. So nothing very important. Air masses resulting in sharp temperature and density contrasts. As you can understand that an air mass is having a constant temperature horizontally. Okay. Now, if you have another air mass which has a different temperature horizontally, then when it comes closer, the boundary between these two air masses, there must be a sharp discontinuity. Right? So those regions where there is a boundary of these two air masses are called the fronts, where there is a sharp change. Okay. So what you will find, how will you represent the fronts is that you will have a sharp moisture gradient because relative humidity becomes different. Okay. Next, you will have sharp temperature gradient. Then you have wind shift. Okay. And pressure. Generally, low pressure region you will find rough, which we say. We'll understand this. Okay. Let's define different types of fronts. So fronts are four types: warm front, then you have cold front, then you have stationary front, and finally you have occluded front. Okay, occluded front. So what is a warm front? Is something like this. First is warm front. Okay, warm front is something like this. We represent sign is like this, like semicircle. Okay, this is the front. And what does it represent? That there is a warm air mass here. There is a warm air mass. It doesn't matter what is here. We don't require to see. Warm air mass is here. Some other air mass might be here. And the discontinuity between them is what you call as the warm front. And its direction is this. The front is moving towards this direction. That's why I have made this semicircle over pointing towards the direction of the front. Okay, so this front generally moves from one place to another. Similarly, second is cold front. So how does it look like? Something like this. But instead of semicircle, we draw some triangle. Okay, these are the cold fronts. Again, direction is this. So if I make the cold front's direction like this, the front is moving in this direction. That means front is moving in this direction, but the cold air mass is just behind that. So this is the cold air mass. So in the direction at which the front is moving, in that direction you have to give these triangles or these semicircles, and behind that, just behind that, you have the cold air mass or warm air mass. It doesn't matter what is present in front of it. Sometimes you get warm air mass here, or sometimes you get different air masses. Next is the stationary front. Stationary front. Okay. So how it looks like is something like this. Understood. So you can see that warm air mass is moving in this direction, cold air mass is moving in this direction, and at equal rate. Okay. So there is cold air mass and there is warm air mass. Okay. Warm air mass is moving in this direction, cold is moving in this direction. And at equal rate, so that's why it becomes stationary. It is not moving now. Okay, so this is called the stationary front. And the fourth is what you call as the occluded front. Occluded, the meaning is hidden. Occluded front. Hidden. Occluded means hidden. So how it looks? It looks like this in the same direction. So this is a triangle, then semicircle. Triangle, semicircle, like this. So this is the occluded front symbol. Now what happens is that there is, just like tropical cyclone, there is another thing called the extratropical cyclone, where these frontal disturbances becomes very common. So how it happens is that, so generally low pressure is formed, okay, and there is a warm front and there is a cold front. Okay, this is the warm front. Okay, so we have warm air here, and this is a cold front. So cold air will be behind. What happens is that with time, this cold front, this cold front, try to chase this warm front. So with time, this happens. So okay, let me draw it again. Okay, this is the low, and what happens is that this is what happens. So this is the warm front again, and this is the cold front. So cold front try to chase this warm front, and it lifts because see this is the cold air. If it tries to push this warm air being lighter, okay, this is light in weight, so it goes up. Okay, it's frontal lifting, we call this. While doing this frontal lifting, an occluded front is formed. So occluded front formed, okay, due to lifting of warm air. Okay, and this is how the system develops. Okay, so you can understand that warm moist air, if it is lifted, it becomes cooler and condensed, and cloud formation takes place and rainfall happens. Okay, so let me just write it uh, step by step. Just give you a feel of the extratropical cyclones, how it happens. So cold front tries to catch warm front. Okay. So in this process, in between warm air, that is this, in between warm air gets lifted. Okay, above. Okay, lifted above. Above what? The dense cold air. This leads to condensation. As you can understand, warm air rises and temperature at upper atmosphere is lower, so condensation happens. This results into thunderstorm formation. Okay, so this is the typical steps of the extratropical cycle in a brief overview. Okay, so this is what you have. Okay, next we can discuss about the geostrophic wind in detail, and then we will go to the natural coordinates and try to understand the geostrophy, cyclostrophy, and inertial flow. That's all. That's all for today, and we will stop there. Okay. हाँ, 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 right. तो वहां पे क्यों होता है? क्योंकि जो टेम्परेचर कॉन्ट्रास्ट है ना, वो सबसे ज्यादा है ट्रॉपिक्स में। जैसे हमारे यहाँ पे जैसे ट्रॉपिक्स में इक्वेटर से लेके ट्रॉपिक्स में टेम्परेचर कॉन्ट्रास्ट बहुत कम है। ज्यादा ही होता है ना, हमारे यहाँ पे भी टेम्परेचर ज्यादा ही है, इक्वेटर में भी टेम्परेचर ज्यादा है, ज्यादा कॉन्ट्रास्ट नहीं है। बट जितने इक्वेटर से दूर जाओगे टुवर्ड्स मिड लैटिट्यूड, टुवर्ड्स पोलर रीजन, वो टेम्परेचर कॉन्ट्रास्ट बहुत अच्छे से विजिबल होता है, और उसके वजह से ये सब चीजें फॉर्म होता है। हम लोग आएंगे, आई थिंक नेक्स्ट सेक्शन में ही है, या नेक्स्ट वीक 7 या वीक 8 में है, थर्मल विंड बोल के, जो टेम्परेचर कॉन्ट्रास्ट की वजह से, हाँ, टेम्परेचर कॉन्ट्रास्ट की वजह से कुछ विंड्स ब्लो करते हैं, जो मैंने दिखाया भी था, जेट स्ट्रीम दिखाया था मैंने। वो जेट स्ट्रीम की वजह से ये सब आता है, ये एक्स्ट्रा ट्रॉपिकल साइक्लोन या फ्रंटल डिस्टरबेंसेस, ये सब उसी की वजह से आता है। हाँ, जैसे चाइना में या फिर जापान में कुछ फ्रंटल डिस्टरबेंसेस दिखते हैं मॉनसून के टाइम में, उसको कहते हैं वायु फ्रंट एंड मायू फ्रंट। तो वो सब भी उसी की वजह से ही आता है। हाँ, ये मॉनसून के टाइम होता है, मैं बता रहा हूँ। ठीक है, तो हम लोग आएंगे उसमें, जब आएंगे तो मैं दिखाऊंगा वो सारी चीजें एक साथ। ठीक है। ओके। नेक्स्ट we go to geostrophic wind. We have seen this already, but we have not given details to this geostrophic winds. Okay, so it's, we have already seen that it is a diagnostic balance. Okay, the diagnostic balance of pressure gradient force, pressure gradient force, and Coriolis. Okay, so how does it look like? Any other forces are not present. So zero, du dt is zero. minus 1 by rho delta p delta x, and all are in the horizontal direction, so it should be plus fv. Similarly, v momentum equation, that is meridional one, this should be 0 because no other terms are present. Delta p delta y minus f of u. This is what you have. Okay, and we can replace this balance. So v is equal to vg and u is equal to ug. So what will be your vg therefore? It will be 1 upon rho f delta p delta x. This is your vg, the meridional geostrophic wind. Similarly, your ug, zonal geostrophic wind, will be 1 upon rho f with a negative sign delta p delta y. Interesting fact is that the zonal geostrophic wind is dependent on the meridional gradient of the pressure, but meridional geostrophic wind depends on the zonal gradient of the pressure. This is very opposite. Okay. Now, in total, if you combine in vector form, Vg, the total net vector, can be written as Ug I cap, Ug I hat plus Vg j hat. Right? So, can I write this as 1 upon rho f? Okay. You can take a negative sign, that's okay. Delta p by delta y I hat plus, or it should be minus actually, delta p delta x j hat. Okay, let me make this I hat j hat k hat for the cross product case. Okay, minus 1 upon rho. Okay, delta p delta y. Can we write this I hat as minus k cross j? Because if I do k cross j, it will be minus I. Okay, so can I write this as with a negative sign k cross j? Similarly, delta p delta x, the j, can we write it as p cross I with a positive sign? We can. So now take the negative sign outside. So 1 upon rho s, we are getting delta p by delta 1 k cross j plus delta p by delta x k cross. Okay, then 1 upon rho f. Take the k cross out and you get delta p delta x I hat plus delta p delta y j hat. So finally, my geostrophic wind in vector form can be written like this. Can I write this as grad p? Yes, horizontally. Remember these. So the geostrophic vector, wind vector can be written like this. Okay. So this is the geostrophic wind vector. So it consists of both sign as well as wind vector. Okay. It consists of both sign as well as the magnitude. So how we can say that? Suppose you have isobars like this. Isobars means lines of constant pressure, surface of constant pressure. I'm writing as line. So this is P1, this is P2. Okay, and I'm saying that P1 is less than P2. Okay, and it is northern hemisphere. What does that mean? Northern hemisphere means what? Which quantity will change in the northern hemisphere? F. Correct, because F depends on the latitude. Latitude in southern hemisphere is negative, but northern hemisphere is positive. So F is greater than 0. Why? Because F is equal to 2 omega sine phi. Sine of positive pi is always positive. So it is greater than 0. So F is greater than 0. Right? Grad P. Remember, gradient, the direction of gradient is a vector, remember. So it is a vector and its direction is always from low to high. Low to high. This should be the direction. So grad P, its direction should be therefore P1 is less than P2. It should be from low to high. This is the direction of grad P. Okay. Now, this is suppose your some xy plane. So the z vector should be upward, that is coming out of the pole. So let me change the color. This should be the k hat direction. Okay. Now, if this is the k hat direction, then k cross grad t will be, so the net, that is k cross grad t should be this. This should be the direction. Right hand thumb rule, if you can use, k cross grad t will be this. So this should be the direction of the vg vector. Okay. So what we can see that in the northern hemisphere, the geostrophic wind blows parallel to the pressure surfaces, but it keeps the low pressure region to its left. So in northern hemisphere, geostrophic wind blows in such a way that to its left, pressure surface P is lower. Okay, so this is one of the cases. Similarly, if you now take southern hemisphere, it will be opposite. Simple. So for southern hemisphere, low pressure will be to its right. And what will change that in the formula? F. F becomes negative. So there is an extra negative sign which makes it here. That's the thing. Okay. So this is the geostrophic part. Okay. Another important thing. Remember this, that this is away from the equator. Geostrophic wind is important. Why not at the equator? You know that F is nearly zero. There is no meaning of geostrophy there. Okay. Away from the equator. So away from the equator, geostrophy, geostrophy exists. Geostrophic balance exists. All right. So this is one of the important things. I can also show you by going into the windy, maybe. Let's see. Yeah, this part, that over the Arabian Sea, you can see that there is a uh, west to east flow. That is near geostrophy. Cannot exactly say that is a geostrophy. It is a near geostrophy. Okay, where low pressure, as you can see, mostly the low pressure is towards this uh, northern Indian region, Pakistan, and Saudi Arabia, this region, and relatively higher pressure is present over this region, southern Indian Ocean. So that's why you get a near geostrophic flow. It's not a complete geostrophic. So this is one of the examples. But if you go more towards the north, you will get much more geostrophic balances. Okay, so this is one of the examples. Okay, it's already 7:30. Okay, let us discuss about a couple of more things and stop the session. Okay, one is the natural coordinate. This is its derivation can be found in the lecture series, so I'm not doing it. Coordinates. Okay, so what does it represent is that it's just a simple coordinate system that if your wind is moving like this, okay, the direction of the motion is the tangential vector or s hat, and leftward normal to that is your n hat, the normal. N hat is the leftward normal vector. This is a convention, normal vector. People can take right one, but generally leftward is taken as a convention. And S hat is the direction of unit vector in the direction of winds or motion. Okay, so this is the thing, and K hat is always the vertical direction. This is there is no change in the vertical direction. Okay, so this is the difference in the natural coordinate, and the equation can be derived, but I am not deriving it. So it's dv dt is minus 1 by rho delta p delta s, that is in the direction of the motion, and v square by r, the centrifugal force, the Coriolis force is v plus 1 by rho delta p delta n should be equal to 0. These are the two equations which we use in the natural coordinate system. Okay, this is the thing, and let me see what else we have. Okay, so this is the n hat equation. This is the s hat equation. As you know, with in the direction of the motion, you don't find the centrifugal force. Neither you find the this Coriolis force. Coriolis force always acts perpendicular to the direction of motion. So that's why it is in the n hat direction. And centrifugal force also. So suppose you have a disk and if you have a mass here, if it is moving also in any direction, centrifugal force will pull it to its mostly to its perpendicular direction. So that is what is being told here. Okay. And okay. Now in this natural coordinate system, how we can write the geostrophic wind? Geostrophic wind in natural coordinates. Remember. Okay. So TVDT, as you know, in the geographic wind we have already discussed, do we find any pressure gradient in the direction of the wind? So suppose this is your VG, it is P1 and P2, and P1 is less than P2, it is northern hemisphere. So is there any pressure gradient in the direction of the wind? No. It is perpendicular, right? Grad P is perpendicular to the direction of the wind. So dVdt is 0. But okay, V square by R plus FV definitely, and there is a pressure gradient in the normal direction, normal to the direction of the motion. So this is equal to 0. But these isobars, so isobars are straight isobars. That is, no curvature is there. Okay, no curvature. If there is no curvature, then R will tend to infinity. No curvature, so there is no point of center from where you will find the radius of the curvature. So R tends to infinity, this term vanishes. This thing is that, or if you have straight two lines, there is no circular motion, right? So how can centrifugal force come? It will not come. So only these two will be the balance. So it's your V, therefore G becomes 1 by rho L minus delta P delta. And this is the exact expression what we have got in the when we were deriving the geostrophic means. Almost similar, right? But based on your S hat and N hat, you get a negative sign and something like that. Okay, this is how the geostrophic wind looks like. There is another wind which is called the gradient wind, which we will come later in the next session. But let us discuss another flow, which is called the inertial flow. This is the inertial flow. Inertial flow is the balance between inertial forces like the Coriolis, the pseudo forces, Coriolis and centrifugal. Again, in this case, you will find the normal vector equations are important. So v square by r plus fv, but there is no pressure gradient, so you can ignore that. So what you get? V 1 plus for this V by R plus F. That is equal to 0. So either V is 0 or V is equal to minus F into R. These are the two possibilities you have. Okay. Let us check this possibility because this 0 is a trivial solution. So R is equal to minus V by F. Okay. So F is negative in the southern hemisphere, makes this positive based on the velocity direction. Okay. So in northern hemisphere, F is greater than 0. If now V is greater than 0, then your R is negative. R negative means, sorry, R negative means that the center is to the left of the motion. So this is C. So motion is here. Sorry, to its right. R less than 0 means center is to the right of right of motion. So if the motion is like this, center is to its right. Right means you if you point your direction, you yourself sit on this arrow at this arrow to its right, and center will come. That is the meaning of R less than 0. So this is how it looks like. And if you see that this is the motion, then it is kind of a high in between. But here the high and low case is not there because there is no pressure gradient. Okay, so this is how it looks like. Similarly, if V is less than 0, then R is greater than 0. In that case, things changes. This is your motion, this is your center. So R is greater than 0. Okay. So this is how it looks like. And the time period of these kinds of emotion is 2 pi R divided by V, which can be written as 2 pi by F, which is about half pendulum. All right, this is the thing. And the third one is the cyclostrophy. Cyclostrophic wind is the balance between pressure gradient and centrifugal. So this is the balance between pressure gradient and centrifugal forces. So simply, in a normal equation, you have V square by R plus 1 by rho delta P delta N. No Coriolis, okay, nothing. So this is what you get. So what will be the solution of this? It will be minus R by rho delta P delta N with a root. And you know that if R is greater than 0 and delta P delta N is greater than 0, or if R is less than 0, delta P delta N is less than 0, then V is root of negative value, which is not possible. Imaginary. Okay? Not possible. Imaginary. Not a real situation. So these two will not exist, but other two conditions can exist. So first condition therefore is R greater than 0, delta P delta N should be less than 0. Let's see how it looks like. R greater than 0. That means center is to the left of the motion. So make a circle. This should be your, um, suppose the direction of motion, C is to its left. So this is the thing. Also, N is the leftward normal. So this is the N hat direction. Okay. In the N hat direction, pressure decreases. So it becomes low. Here it may be high. So you can see that around the low pressure system, there is a cyclonic circulation. So simply cyclonic circulation around the low. And what is the second condition? R is less than 0. and delta P delta N is greater than 0. So R is less than 0 is something like this. Okay. And again, left normal is towards left. So this is your left. Right? So this is now the positive z direction. We increase this in this direction. So this is high, this is low. Okay. So it is anti-cyclonic circulation around a low pressure system. This is not generally visible, but this is a mathematical solution. Sometimes it might be visible. Okay, so these are the couple of things. And the last thing is the Rossby number. And after doing this, let me see whether in the next assignment, assignment 7, there is some typical questions are there or not. So I will just quickly give you some hints of those assignment questions. Okay, R naught we have already defined earlier, like the inertial to the Coriolis force. Another way to define is the centrifugal to Coriolis. This is another definition. Okay, same thing will come, that is V upon RF. Same thing. So if centrifugal becomes much more dominant over Coriolis, then your R naught is large. And in that case, we generally have cyclostrophic wind. Why cyclostrophic wind? Because cyclostrophic wind does not have Coriolis. Okay, this is the first condition. Second condition, if Coriolis is much higher than centrifugal, R naught is smaller, and we know, we have seen that when R naught tends to 0, we get what? Geostrophic. Okay, so geostrophic wind is generally associated with smaller R naught or 0 R naught, and centrifugal wind becomes important, R naught becomes large, cyclostrophic winds falls. That's a typical thing which I wanted to show. Okay, let me see in assignment, 7th week assignment, there any big things are there or not. Mm, yeah, one thing. Anyway. Okay, what I remember is that I have seen one question in assignment 7 where density is given in kg per cc. That is wrong. The unit should be kg per meter cube. Question value is absolutely fine. Don't use kg per cc. It should be kg per meter cube. Okay. As per what I have solved, I have seen that it should be kg per meter cube. Any one of the questions, I am not very sure. Okay. Some assignment 7. Some question is there. Not very sure which one. All right. This is one of the things. Let me see whether anything else is there. Because if you use this centimeter cube thing, it will not come out to be correct. Okay. What else? Okay. Another thing is that geostrophy. Okay. Geostrophy, remember, is Vg in pressure coordinate, that is xy coordinate is 1 by a. So suppose this is the meridional one. Let me write 1 by a delta phi by delta x. This is the meridional one. Okay, the north south one. Similarly, zonal will be minus 1 by f delta phi delta 1. Let me write it. Minus 1 by f delta phi delta 1. Okay. Remember, this phi is g times z. Z is the geopotential height. Geopotential height. Okay. So your Vg will be therefore g by a delta z delta x. Just remember this because I think some questions might have this thing. Okay. There is also another question which is ship weighing measurement kind of a question. Okay. So just so this ship question in here. So I will just give you a hint that is the weather ship, okay, it gives you the information of the local rate of change of temperature. But sorry, rate of change of pressure. Change of pressure. That is delta P delta T. But all other ship, all other ships, okay, like the ship one and ship two, whatever the change in temperature they are getting, that is dPdt, the total rate. Okay, use that and try to solve. So it will use generally this thing. dPdt is equal to delta P delta T, okay, plus V dot grad. Use this and you will be able to understand. Do it for ship one, do it for ship two, and try to find out what will be the geostrophic wind. Okay, so this is one of the things. What else? What else? Let me see. Nothing much. Yes. Another thing is that the divergence of the geostrophic wind. There is another question. Divergence of geostrophic. Okay. So Vg, we know that it is minus 1 by rho f delta p delta y I hat plus 1 by rho f delta p delta x j hat. Okay. Just remember one thing. When you do del dot bg, that means what? You will be doing this, right? Delta delta x minus 1 by rho f delta p delta x. Sorry, delta y plus delta delta y of the I hat and j hat will go because it's a vectorial thing. You can understand delta delta y. Okay. Just remember delta f by delta y is not equal to 0. Delta f delta x can be taken as 0. There is no variation of f with x, but variation of with y you cannot ignore. So how will you do it? So can you write delta f delta y as delta f divided by this is the radius of the earth, delta phi, the latitude, right? With this we can write this is your delta phi, okay, and this is your delta y. You can write this. This is your a, okay, and f you can this is 2 omega sine phi. So while doing this process, use this, and you will get the answer. Okay, okay. Just I think this is fine. Just use all these concepts for the assignment question. Okay, this is one, this is the second, this is the third, and this is the fourth. Okay, these couple of things if you can use, then I think assignment questions will be easily solved. Okay, other things we have already discussed. I think we can end today. Next Tuesday we will meet. Okay, other questions written. Okay.